Hello everyone, today we're going to be doing 2013 Aime I Problem 11. Miss Matt's kindergarten class has 16 registered students. The classroom has a very large number, n, of play blocks which satisfies the conditions. A. If 16, 15, or 14 students are present in the class, then in each case all the blocks can be distributed in equal numbers to each student. And B. There are three integers x, y, z that are strictly in between 0 and 14 and are distinct, such that x, y, z, if x, y, z students are present and the blocks are distributed evenly, then there are 3 blocks remaining. Find the sum of the distinct prime divisors of the least possible value of n, satisfying the above conditions. So, first by condition A, we know that n is a multiple of the LCM of 16, 15, and 14. So we know that 16 is equal to 2 to the power of 4, 15 is equal to 3 times 5, and 14 is equal to 2 times 7. So the LCM is going to be 2 to the power of 4 times 3 times 5 times 7, which is equal to 1,680. Now, by the second condition, we have that when you take n and you divide it by x, y, or z, you're going to get a remainder of 3. That means that when you do n minus 3, that number is going to be divisible by x, y, and z. So that means we have, oh, by the way, this is, you have, n is a multiple of the LCM, so it's 1680 m is equal to n, where m is just any integer. Okay, so yeah, now back to part B. By this, we can get that n is also equal to some multiple of the LCM of x, y, z plus 3. So let's look at what x, y, and z could be. Since they're saying that there's a remainder of 3, we know that x, y, z obviously have to be greater than 3, because you can't have like 3 people and have a remainder of 3, because that's obviously, you can evenly distribute those 3 blocks. So that means we can just restrict our range further to make it 3 is less than x, which is less than y, which is less than z, which is less than 14. So listing out all the possible integers within this, we have 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And then now we focus on this. How do we know which of these numbers to choose? Well, we have this LCM plus 3. So if we want this entire thing to be a multiple of 16, this cannot be a multiple of 2, because adding 3 to that will make it odd. So that means we can cancel all multiples of 2. Same reasoning for 5 and 7, because if we have the LCM is a multiple of 7, then adding 3 to it makes it not a multiple of 7 anymore. Same for 7. But it's different for 3, because if you have a multiple of 3, if this is a multiple of 3, and you add 3 to that, that's still going to be a multiple of 3. So the only numbers that we cannot have for x, y, and z are multiples of 2, 5, and 7. So let's go back here and cancel all the multiples of 2, 5, and 7. So canceling out all the 2's, and then the 5, and then 10 is already a multiple that we canceled out, and 7 gets canceled out. Oh, now we only have 3 numbers left. And these obviously will be x, y, and z, respectively. So now we have our values for x, y, and z. That means our LCM will be 9 times 11 times 13, which is 1287. Now we'll just do some modular arithmetic. So we're gonna divide this up into 16, 3, 5, and 7. So we'll say 1287k plus 3 is equal to 0 mod 16. It's also 0 mod 3. It's also 0 mod 5, and then 0 mod 7. So first of all, we obviously know that this is true because 1287 is a multiple of 3, and you can basically just factor out the 3 here, so this we don't have to worry about. Next, let's look at this one. We have that 1287 ends with a 7, and then we're taking a multiple of that and adding 3. So the multiple of 5 can either end with a 0 or a 5, but then because we know that n is even, it cannot end with 5, so it has to end with 0, which means that k is 1 mod 10. Because then you'll just have, with the last digits, you'll have 7 plus 3, which gives you a last digit of 0. So this has been accounted for. Next, we can look at mod 16. So 1287 mod 16 is just 7, so you have 7k plus 3. Now let's take the numbers and let's just start with 0 and plug in the numbers until we get that 7k plus 3 is a multiple of 16. While doing this, we get that the smallest number of k is k equals 11. So that means we have k is equal to 11 mod 16. Combining these together, we get k is equal to 11 mod 80. Okay, so we accounted for that. This is the last one now. We take 1287 mod 7, which gives you 6. So you want to plug in some number k such that 6k plus 3 is a multiple of 7. So we look at this and take the first few numbers that satisfy that, which are 11, 91, 171, 251, and so on. If we plug in 11 for k first, then we get 69, which is not divisible by 7, so that's not it. 91 is already divisible by 7, so plugging that in gives you 3, but that's not divisible by 7. 171 is 3 mod 7, so when you plug in, so that's like basically plugging in 3 for k, which gives you 18 plus 3, which is 21, which is divisible by 7. So that means that our smallest value for k is 171. So now all we have to do is plug in k for our expression to solve for n, and then find the prime divisors of that. So now it's just pretty much straightforward computation. we have 1287 times 171 plus 3. So let's multiply this out. So n is equal to 220,080. So now let's prime factorize that. This is just the way I prime factorize it, so you can just ignore that. You can do it however you do it. We can divide by 3 to get 917. Divide by 7, and that gives you 131, which is a prime number. So our prime divisors, our prime factors, we're only adding each one once, so that means we're not like repeating them. So our distinct prime factors are 2, 5, 3, 7, and 131. So that means we can just add them to get our final answer. So that gives us 10, that gives us 17, and then we finally have 131 plus 17, which is 148. And that is our answer. Thank you for watching. Have a nice day.